thinking about just one idea here, and that's the Doppler effect, which basically means that if the source of a wave is moving, or if the source is stationary, but something receiving the wave, observing the wave is moving, or if both of them are moving, then the kind of wave that the observer actually perceives is different from what it would have been if everything had been stationary. But, everybody is familiar with the Doppler effect. If you hear an ambulance siren from far away, if that you're standing still on the street corner, the ambulance is approaching you, you hear the ambulance siren at one frequency, and if the ambulance passes you, now the ambulance is moving away from you, you hear that siren all of a sudden at a different, lower frequency. That's the Doppler effect. And as you see in that example, you get different Doppler effects depending on whether the source and observer are getting closer together or the source and observer are getting farther apart. Here's a simple example of why that works. Imagine that there's an observer of some kind of wave over here. To be concrete, let's call it a sound wave. And the source of that sound wave is moving right to left towards the observer. And that source puts out a signal at regular intervals. Every time the source goes through one cycle, it puts out a new signal. So at time 0, the source is right here, and then in one period of oscillation, the source moves a little bit, and having gone through one period, that's the time to put out the second signal. Now in the capital T seconds, right, the period, the source has moved this far, just the speed of the source times the length of time, which is one period. Now, the source put out a signal here at this moment, and then in this much time, the source traveled this far. So the first signal, the first pulse that the source put out is now right here at this location. That's what the solid dots here will symbolize the different pulses emitted by the source. And I label that as 0 because that's the pulse that was emitted by the source at time 0 when the source was right here. And then you wait a length of time equal to one more period, right, 2 periods after the start, and the source has moved another distance equal to speed of the source times the elapsed time. But in that time between here and here, the pulse that was emitted from this point, source was at this point when it emitted the second pulse, has traveled at the same speed the first pulse traveled, so it'll travel the same distance. The first pulse was emitted here, and then it moved 1, 2, 3, 4 steps. The second pulse was emitted here, and since it goes at the same speed, it'll move 4 steps also. 1, 2, 3, 4. And here's where that pulse that was emitted at time t, here's where that pulse is now at time 2t. At time 2t, the source is right here, and the pulse that was emitted one cycle earlier when the source was here is now here, and the pulse that was emitted 2 cycles earlier when the source was way back here at the start has moved 4 steps during the first cycle and then 4 more steps during the second cycle. So now at time 2t, the source is here. The first pulse to be emitted has traveled this far, and the pulse that was emitted 1 cycle later hasn't had as much time to travel, so it's traveled a shorter distance. And then, of course, at this time, another cycle has been completed, so another pulse is emitted, and then wait 1 more cycle, go from 2t to 3t, and now the source is right here, and it has traveled again a distance vs times t, and the pulse that was emitted when the source was here travels at the same speed, so in the same amount of time, 1 period, it travels the same distance, 4 steps. So 1, 2, 3, 4. This pulse, which I call 2t because it was emitted when the source was here at time 2t, this pulse has traveled 4 steps from the point where it was emitted back here. And meanwhile, every other pulse has traveled the same distance compared to where it was at 2t. So the t pulse was here at 2t, and then at time 3t, it'll be 4 steps farther down. 1, 2, 3, 4. So here's where the pulse t is at time 3t. Here's where pulse 2t is at time 3t, and pulse 0 has now gone past the observer. But now notice one thing. From the observer's point of view, the spacing between equivalent states in the wave, is just a long name for wavelength. The spacing between equivalent states is this big, 3 steps, whereas now look at this top line, which I haven't talked about until now. If the source had been stationary all the time, then it would have put out a pulse right at the start, and then it would travel at the same speed as always, so in 1 period it would travel 4 steps, and then in a second period it would travel 4 more steps. So the very first pulse emitted from here, now we're imagining stationary observer, emitted here, and then you wait t seconds, so it travels at the same speed as any other pulse. All these different things are the same wave through the same medium, so they've got the same speed. Moves 4 steps in a period, so it would move here, and then during the second cycle, it would move here. And meanwhile, in that second cycle, right at the beginning of the second cycle, a second pulse would be emitted, and during that second cycle, it would move from there, where the stationary source is located, to here. So in other words, if the source had been stationary, an observer over here would perceive the pulses as farther apart than they are here in this case, because the pulses here are closer together because the source was moving towards the observer. So the pulses are farther apart, are closer together, but they're still moving at the same speed as always. So the frequency with which pulses arrive at the observer will be higher. And that's a Doppler effect. And mathematically, algebraically, what does that look like? Well, basically all we need to do is use the fundamental equation for traveling waves and then do some algebra. Notice one thing though, the normal wavelength, if the source of these pulses had been stationary, is longer, and the wavelength that we get when the source is moving towards the observer is shorter, and the distance between that, or the difference between that longer wavelength, 4 spaces, and the shorter wavelength, 3 spaces, that's a difference of 1 space. But how big is that space? That's just this distance here, the distance that the source travels in one period of oscillation. So let's say that algebraically. If you want to think a little bit more about all that diagram that was on the blackboard, stop and move back in time and look at it again. So the wavelength, the longer wavelength that we got when the source was stationary, is bigger than the shorter wavelength that the waves have when the source is moving. And that difference was, just as I said, this distance here, the distance that the source moves in one cycle, which is just velocity of the source times one period. Period and frequency are inverses of each other, so let me write this as velocity of the source divided by f0. F0 is what we will call the frequency of oscillations at the source. So in other words, our basic equation that connects wave speed, frequency, and wavelength is like that. I'll write VW to distinguish it from the other velocity that we'll have here, source velocity. So this is the same whether the source is moving or not, because remember, wave velocity depends only on the medium through which the wave is traveling. If this is a sound wave, the waves are all traveling through the same air, whether the source is moving or stationary. So the air is the medium, the air doesn't change, so the wave speed doesn't change. So rewrite this equation. This equation could relate either the frequency of the source, the wave speed, and the wavelength that you get if the wave is stationary, or it could just as easily relate to the different frequency that you get when those pulses traveling at the same speed, the same VW, are now closer together with that smaller wavelength that I call wavelength prime. So that's all I need here to get a nice algebraic statement of how much the perceived frequency, right? This is the frequency that that an observer would measure, because this is the wavelength that that observer over there on the left would measure. So I can just rewrite all this a little bit and rewrite this. Lambda is just equal to wave speed over frequency. So then let me rewrite this. Lambda minus lambda prime is just that. Wave speed over frequency of the source minus lambda prime, wave speed over a perceived frequency, and that's equal to this, source speed over frequency of the source. Do a little bit of rearranging there. Put both of the source frequency, the F0 terms, on the same side of the equation. Move this to the other side of the equation, and then we have VW over F0 minus V source over F0 equals velocity of the wave divided by perceived frequency of the wave. Invert the whole equation. The inverse of the left-hand side will equal the inverse of the right-hand side. You can make the left-hand side a little simpler by factoring out a factor of 1 over F0. So we have that. Now invert the whole equation. F0, this is now F0 over wave speed minus source speed equals perceived frequency over wave speed. And then simplify this by, imagine multiplying both sides of the equation by 1 over V wave. So you'll have here in the denominator V wave times 1 over V wave, just plain 1. Then do the same over here. 1 over V wave. So this times 1 over V wave is just 1. This times 1 over V wave is minus V source over V wave. So relatively simple, handy equation that you can actually interpret and make sense out of. Now the simplified version of the right-hand side is just source frequency 1 minus source speed over wave speed equals, on the right-hand side, nothing but the perceived frequency. So notice, if the source is stationary, that means the denominator here is just plain 1, and the perceived frequency is the same as the source frequency. There's no Doppler effect. If the source frequency is not 0, if the source is moving, then this term is not 0, so you're subtracting something from 1. So now this denominator is less than it had been before. When the source speed was 0, this denominator was 1. Now it's less than 1. So when the denominator is smaller, this entire quotient will be larger, which means the perceived frequency is higher. Perceived frequency is higher than the actual frequency with which vibrations are happening at the source. That's a Doppler effect. And as you saw in the text, and we'll think about it a little more in class, if instead of source moving closer to observer, the source was moving away from the observer, you get the opposite effect, and the perceived frequency would be less than the source frequency. F prime would be less than F0. Let's look at one other thing here to give you something to think about. Let's imagine you're listening to some sound coming from a moving source. You're standing still and the source is moving, so it's just like what I've been talking about here. And as time goes by, you hear that frequency change a little bit. So it's a graph of the perceived frequency, the frequency you hear, as a function of time, and the actual frequency of the source would be this value. And let's say as time goes by, you hear a perceived frequency like this, constant for a while, and then a rising frequency, and then a dropping frequency. And we'll call those three different situations A, B, C. Well, in situation A, obviously, f prime is staying constant. The perceived frequency is staying constant, which means all these numbers on the left-hand side are staying constant as well. In particular, the source has a constant velocity. But since the perceived frequency is greater than the actual frequency of the source, we know the source is actually moving, but it's moving at a constant velocity. There is motion of the source, so there is a Doppler effect, but it's a constant Doppler effect because what the source is doing isn't changing. Region B, the perceived frequency is increasing. Well, the perceived frequency is increasing, so something here on the left-hand side has to be changing. Presumably the same thing is happening all the time at the source. The source is oscillating the same way all the time, so the actual frequency of oscillations at the source isn't going to change. It's the same kind of wave moving through the same kind of sound wave moving through the same kind of air. The medium isn't changed, so the velocity of the wave is not changed. The only thing that could change is the speed of the source. And in this case, getting this kind of a change in f prime in the perceived frequency, it's changing because the source is speeding up. Just think about it algebraically first. Source is speeding up, so this gets larger. So this fraction here gets larger, which means you're subtracting a larger number from 1. You're subtracting more from 1 than you were before, which means less is left over. In other words, this denominator gets smaller when speed of the source gets bigger. And as the denominator gets smaller and smaller, the overall fraction gets bigger and bigger. Perceived frequency gets higher and higher. Like that. Or to put it another way, you have a Doppler effect because the source is moving. If it's moving more and more dramatically, in other words, faster and faster, you get a more dramatic Doppler effect. And then in region C, just the opposite of what was happening in region B. The source is slowing down. This is decreasing, so this fraction is decreasing, so you're subtracting less and less from 1, leaving more and more left over after the subtraction. In other words, as this gets smaller, less is subtracted from 1, so this gets smaller and smaller, so the denominator gets bigger. When the denominator gets bigger, the whole fraction gets smaller. The perceived frequency decreases. Or to put it another way, sort of like I said before, just kind of flipped around, you have a Doppler effect because the source is moving. So if there's less motion to the source, you get less of a Doppler effect. But, less of a Doppler effect, meaning that the perceived frequency gets closer and closer to the actual frequency of the source. Less Doppler effect, meaning there's less of a difference between the perceived frequency and the frequency of the source. More and more Doppler effect, meaning there's a bigger difference between the perceived frequency and the frequency of the source. So we'll think about this more in class, on specifically how say the Doppler effect can be used to measure the speed of a speeding car, or the speed of a baseball when it's thrown by the pitcher, or the speed of galaxies moving through space.